Hello, myself Dr. Rohit Kumar Verma, Assistant Professor Maths, Government Chandulal Chandrakar College, Patan. In this lecture, we will study about uniform boundedness principle or Banach Steinhaus theorem. This chapter is related to functional analysis, paper 1, M.Sc 4th semester, unit number 1, namely नॉर्मल लीनियर स्पेस। जैसा कि हम जानते हैं कि बेनाक स्टीनहास थ्योरम या यूनिफॉर्म बाउंडेडनेस थ्योरम एक बहुत ही महत्वपूर्ण फंडामेंटल थ्योरम है और इसके बहुत सारे एप्लीकेशंस हैं, जैसे द एग्जिस्टेंस ऑफ कंटिन्यूअस पीरियाडिक फंक्शन हुज फोरियर सीरीज डाइवर्जेस एट अ गिवन पॉइंट, और दूसरा एप्लीकेशन स्टडी ऑफ मैट्रिक्स ट्रांसफॉर्मेशन इन सीक्वेंस स्पेस। बेनाक स्टीनहास थ्योरम का जो वेरिएंट है वह यूनिफॉर्म बाउंडेडनेस थ्योरम कहलाता है। द यूनिफॉर्म बाउंडेडनेस थ्योरम was first discovered in 1908 by H.L. Liebeck during his investigation concerning the Fourier series, but this was given in general form by Stephen Banach and H. Steinhaus in 1927. Now we state the uniform boundedness theorem और बेनाक स्टीनहास थ्योरम। इस थ्योरम के विभिन्न प्रकार के स्टेटमेंट्स हैं जो कि एक के बाद एक मैं इस प्रकार से कहते जा रहा हूँ। लेट टी आई बी ए सीक्वेंस बी अ नॉन वाइड फैमिली ऑफ बाउंडेड लीनियर ट्रांसफॉर्मेशन from a Banach space X into a normed linear space Y. If the condition supremum I norm Tix less than infinity for all x in X holds, then supremum I norm Ti less than infinity. Or another statement, let X be a Banach space and let Y be a normed space over the field K. If F is the set of bounded linear operators from X into Y as is point-wise bounded, then it is uniformly bounded. Another statement is as follows. Let X be a Banach space and let Y be a normed linear space. Let Ti be a non-empty set of continuous linear transformation from set X into Y such that sequence Tix is bounded for each small x in capital X, then sequence norm Ti is bounded. Proof. For each positive integer n, define a set Fn is equal to point X such that X belongs to X and norm Tix is less than n for all I. Then this Fn is closed subset of X and X equal to infinite union of Fn. Since X is complete by the bare category theorem, one of the subsequents, say Fn0 of Fn, has a non-empty interior. Thus Fn0 contains a closed sphere S0 whose center is x0 and the radius is, say, r0, which is positive. Hence each vector in each of the sets Ti S0 has norm less than or equal to n0, that is norm Tix less than equal n0 for x belongs to S0 and I equal to 1 to 3, etc. We write this as norm Ti of S less than equal n0 for I equal to 1 to 3. Since x0 is a closed sphere with center x0 and radius r0, the subset S0 minus x0 divided by r0 is the closed unit sphere, say S. Since x0 belongs to S, it is evident that norm Ti S0 minus x0 less than equal to n0. This yields norm Ti of S strictly less than 2n0 by r0. Hence ti less than equal to n0 by r0 for every I equal to 1, 2, 3, etc. This implies that sequence ti is bounded. This completes the proof of the theorem. इसी थ्योरम को एक नॉन टोपोलॉजिकल प्रूफ के रूप में भी दिया जा सकता है। इसके लिए स्टेटमेंट इस प्रकार है कि चूँकि हमें सिद्ध करना था सुप्रीमम नॉर्म टी आई एक्स स्ट्रिक्टली लेस देन इन्फिनिटी, देन सुप्रीमम आई नॉर्म टी आई लेस देन infinity, or if ti x is bounded, then norm ti is bounded. We will prove its contrapositive statement, that is, if norm ti is unbounded, then norm tn is unbounded also. Where sequence tn is a subset of sequence ti, this method was used by Hennefield in 1980. Proof of the non-topological proof of the Banach-Steinhaus theorem proof. Contrary, let norm ti is unbounded. We will construct a sequence xn in X set and a sequence tn from ti I equal to 1 to infinity, so that norm xn is equal to 1 by 4n, equation A, and so that for x equal to n equal to 1 to infinity xn, equation B, norm tnx greater than n for each n. Now suppose that x1, x2, xn minus 1, t1, t2, tn minus 1 we have already been selected. Further, let m of n minus 1 is equal to supremum I norm ti x1 plus x2 plus dash dash xn minus 1, equation C. Next we select tn, so that norm tn is strictly greater than 3 into 4 power n mn minus 1 plus n, equation number D. Then we select xn of norm 1 by 4n, so that norm tn xn is strictly greater than 2 by 3 tn xn norm tn norm. This is strictly greater than 2 by 3 into 4n mn minus 1 plus n into 1 by 4n, replacing tn from D and xn from equation number A. This implies tn xn is strictly greater than 2 times mn minus 1 plus n. Call this equation number 1. And norm tn xn plus 1 plus xn plus 2 plus dash dash less than equal half norm tn xn. Call this equation number 2. By the triangle inequality and from equation 1 and 2 above, we get norm tnx greater than equal tnx xn norm minus norm tn xn plus 1 xn plus 2 plus dash dash minus tn bracket x1 plus x2 plus xn minus 1. This is greater than or equal to half tn xn from equation number 2 here, with tn xn plus 1. This is replaced by this with tn xn. There this is greater than equal to half tn xn minus norm tn xn plus 1 plus dash dash dash. This is strictly greater than mn minus 1 plus n by equation number C here, minus mn minus 1. This is equal to n. Hence we conclude that norm tnx greater than n for each n. Thus, if norm ti is unbounded, then norm tnx is unbounded. This completes the proof by contrapositive rule. Remark: Banach-Steinhaus theorem need not be true if x is not complete. तो completeness ही इसका नेसेसरी कंडीशन है Banach-Steinhaus theorem के सही होने के लिए. ये हम एक काउंटर एग्जाम्पल से दिखाएंगे. एग्जाम्पल: लेट x इक्वल टू ए पॉइंट x which is made of x1, x2, xn 0, 0, 0 etc. where xi are real and I is natural number. Then x is a subset of L2. Now define xn is a mapping from set x to L2. here X is not complete and L2 is a normed linear space. Now Tn is defined by Tn of Ei is equal to 0 if I not equal to n, and n En if I equal to n, where Ei is a sequence with 1 in the ith place and 0 elsewhere. That, for example, E1 equal to 1 0 0 0 etc., E2 equal to 0 1 0 0 0 etc. Then for x equal to I equal to 1 to k xi ei, Tnx equal to 0 for n greater than k. This implies that supremum I less than equal n strictly less than infinity, norm Tnx is finite. But we observe that norm Tn is n and supremum I less than equal n less than infinity, norm Tn is infinity, which is unbounded. Thus, the completeness of domain space X is necessary. So, we have completed the Banach-Steinhaus theorem, that is uniform boundedness theorem. Thank you.